Hello everyone, my name is Umar, a student of Mechanical Engineering in Institut Teknologi, Bandung, with student ID 131-18248 from class 04 in Structure and Properties of Material class. Today, I would like to present creep phenomena for heat-resisting alloy. Before we move on, we need to know what is creep phenomena. Creep phenomena can be defined as the time-dependent and permanent deformation of materials when subjected to a constant load or stress. Mechanism of creep phenomena can be obtained by a typical creep test, which involves applying a constant load or stress to a specimen at a constant temperature. Here, we have the typical creep curve of strain versus time at a constant load, because creep is receiving a constant load. There are three regions in this curve. The first region is called primary region, which can be typified by a continuously decreasing creep rate. This suggests that the material is experiencing strain hardening in this region. And then for the next one is the secondary creep, or sometimes termed steady state creep. The rate is constant, that's why the plot is become linear. Possibly, this the most important parameter from creep test is the slope of the secondary region. Finally, we have the last part, which is the tertiary. In the last region, there is an acceleration of the creep rate, and ultimate failure will happen in this region at the time, which is TR, when the material become rupture, which is failure. The next, we have creep phenomena curve, increasing stress versus increasing temperature. At a temperature substantially below 0.4 Tm, which is the yellow line here, the strain is virtually independent of time. And then as for the green, blue, and red line, there are certain things that must be noted. First, the instantaneous strain at the time of stress application increase. The second one, the steady state creep rate is increased. And the third one, the rupture lifetime decrease. That's why as the creep strain increase, the rupture lifetime will be decreased. As for the last creep strain, the rupture lifetime will be increased. And then, the result of creep rupture tests are most commonly presented as the logarithm of stress versus the logarithm of rupture lifetime. The first figure here is an example of plot for an S590 alloy, in which a set of linear relationship can be seen to exist at each temperature. There are 4 temperatures here in this graph. And then as for the second figure, is the steady state creep rate for the X, and then versus the stress in megapascal, the Y. As for the steady state creep rate will be explained after this slide. Here we can see the steady state creep rate. As for the first one, is dependent on stress, where the K1 and N are material constant. So the rate will be equal K1 times the sigma to the power of N. As for the second equation is when the temperature is included. And then for QC here is an activation energy of creep, which will be constant. Now we move on to classification of creep mechanism. There are 3 mechanisms that I will explain here. The first, dislocation or power law creep. Second, cobble creep. And the third one, Nabarro shearing creep. As for the first one here, dislocation or power law creep. The strain rate can be determined by the rate at which dislocation are able to climb over obstacle. And then as for the equation that is used to find the rate, you can see here. And then on this side, we have the schematic diagram for power law creep. And then the next one is called Coble diffusion creep. Coble diffusion creep is a diffusion of atom or frequency along the grain boundaries. You can see here in the schematic diagram that the atom or frequency is along the grain boundaries here. And then as for the strain rate can be found using this equation. The next one is called Nabarro shearing. I don't know if it's spelled right. Is the diffusion of atom or frequency through the grain. You can see here in this schematic diagram, and then the strain rate can be found using this equation. The grain boundary is sliding occur in conjunction with the Coble and Nabarro. Next, we have that called Larson-Miller parameter. Is one of the data extrapolation method. This method we need to know to perform, to use this method, we need to perform creep rupture tests at higher temperature under same stress for shorter time exposure. Here is written shorter time exposure, because it's impractical to collect data over long time exposure using this kind of method. And then the equation for a Larson-Miller parameter is this: m equal t times c plus logarithmic tr, where c is constant, t is the temperature in Kelvin, and tr rupture time in hour. And then in the right side here, we have the example of Larson-Miller versus the logarithm of stress for the S590 alloy. There are several factors affects the creep characteristic of metal. These include melting temperature, elastic modulus, and grain size. In general, the larger the grain size, the better a material resistance to creep. The smaller grain permits more grain boundary sliding, result in higher creep rates. And then, the stainless steel and the super alloy are especially resilient to creep and commonly employed in high temperature surface application. Is the example of material just for information. And here we have the example as the turbine blade. Is made of polycrystalline turbine blade, and for the A is made of conventional casting. As you can see here, the rupture is happening. And then B is the columnar grain, and then C single crystal. As we change the method, the creep resistance is increased within time. Sorry, not within time, but the creep resistance is increased. Thank you. That's all from me. Hopefully you have information